So now we've reached the fun part. We've learned the fundamental counting principle. We're really focused on independent events. And then we've also learned ways to talk about when order matters and when order doesn't matter. So those are our permutations and our combinations. So if I just add one new wrinkle, and I want you to think, how many unique ways can we make from the numerals 1, 2, 2, and 3? So we look at these numbers and we see that, well, there's four of them, so it shouldn't be just 4 permute 4, because order matters with numbers. Um, shouldn't it be 24? And the real question goes, can you tell the difference between 1, 2 and another 2? Or specifically, if I write it with one red or orange, and then the second one orange, but as soon as I take away that coloring distinction and then become indistinguishable, I want to know how many are actually indistinguishable. How can I tell those apart? And this happens a lot of times when we have multiples of things or things we can't tell the difference between. So it goes to like, if you can't tell the difference between 1, 2 and another 2, then writing 1, 2, 2, 3 is not any different than 1, 2, 2, 3. So the two numerals that can repeat can be arranged in 2 factorial ways, or 2 then 1. To account for those repeats, what we end up doing in this type of counting rule is we divide by 2 factorial. So ultimately, if we have 4 numbers and 2 of them are indistinguishable, we'll have 4 factorial over 2 factorial, which gives us 12. And you can check if we wanted to list out all 12 of these options, you would see, and trust me, there are no other options to do on this. So with repeating elements, how many ways can you arrange the letters in the word furlough? Well, you would take all of the letters that we have, 1, 2, 3, 4, 5, 6, 7, 8. So we'd have 8 factorial, and then we have to look for any repeats. So I see I have 2 U's, F doesn't repeat, R doesn't repeat, L doesn't repeat, O doesn't repeat, G doesn't repeat, H doesn't repeat. So it would be 8 factorial over 2 factorial. Or 8 permute 8 divided by 2 factorial, whichever way you want to rate it. How many ways can we rearrange the numerals 1, 1, 2, 2, 3, 3? Well, we have 1, 2, 3, 4, 5, 6. We count the total number. That's 6 factorial ways of those. And then we would go 2 factorial for the 1s. We have 2 factorial for the 2s. And we have 2 factorial for the 3s. Each of those repeated or indistinguishable numerals, we have to divide out the repeats. So if we do that, we end up with 90, which is a lot smaller than 720, which is what 6 factorial is. Or, my favorite is, how many ways can you rearrange the letters in Mississippi, or Mississauga if you're from Canada? And it would be 11 factorial, and then we would count the repeats. So we have 4 I's, we have 4 S's, and we have 2 P's. So 11 factorial divided by 4 factorial, 4 factorial, 2 factorial. Note that each of those letters are independent of the other, so we just multiply. And that's how we can start compounding these different events together. So the last one, which is the most interesting, if you want to go down to Greektown or somewhere downtown where they've got a card table, and let's say you can actually go into a casino, you're of that age, or maybe you want to go to Windsor and gamble some money when you turn 18. So what is the probability of getting a full house, kings over 3s, in a 5-card hand? Now, many of you guys go, okay, I think I've played a little poker before. I know I get 5 cards. There are 52 cards in the deck. And the questions that you need to ask yourself is, if you're dealt 5 cards and then you pick them up, does the order matter? Because if order doesn't matter, then this is a combination. And how many different ways you can get 5 cards from a deck of 52 is 52 choose 5. So this number right here is our sample space, or our denominator. These are all of the different ways we can get this. Now the next thing said, I want 3 kings. Well, we need to know that there's 4 kings, and it doesn't matter if you get a heart, then a spade, then a club, or a spade, then a heart, then a club, as long as you have 3 of the same kind. So again, the logic holds that this is a combination. So it'd be 4 kings, and we want to choose 3 of them. Well, that's a lot smaller of a number. It's 4. Likewise, if we know the number of getting 2 3s, there are 4 3s in the deck. We want 2 of them. Doesn't matter what suit they are, so we do 4, choose 2. So if we put this all together, the probability of getting 3 kings and 2 3s, or kings over 3s, is the probability of 3 kings and 2 3s, which is multiplying those two, divided by the total number of ways we can do that. Well, what this turns out to be is 1 over 108,290, or 1 over 108,290, which is a very, very, very small number. Sticking with cards, what's the probability of getting 2 pair? Notice this is a lot less specific, so there must be a higher probability of doing this. So if we're thinking we're getting cards, order doesn't matter. And so if we're thinking about this, the number of ways I could get 5-card hands hasn't changed. So what I'm going to do is on my calculator, I'm going to go and put my denominator in first. So I go to probability. I go to combinations, and I'm going to do 52, 5. Now, we want to get a pair of cards. And so what we first need to do is we need to figure out how many different types of cards are there and choose one of them. So there's ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king. There are 13 different types of cards. And what we want to do is choose one of those. And then once we choose one of those, let's say it's an ace, there's 4 aces, and we want to choose 2 of those. So that would be probability combinations for choose 2. And in all of these, just to enumerate this on my calculator, I'm going to say I'm multiplying. Well, let's say we chose that ace and we got a pair of aces. How many different types of cards are there now? Well, there's 12. It reduced down 1. And how many of those, let's say I want a 5. We would do the same thing. NCR for choose 2. And if I type that into my calculator, and let's just say I take that number and I multiply it by 100, just so we know what this actually is, this would be 0.21% of the time you get 2 pairs of cards, 2 of the same kind of card. Oh, there's something that's missing. My numerator is only saying 13 cards, I want 2 of them. 12 different types of cards, I want 2 of those. Well, how many cards are left if I remove the aces and I remove the 3s? Well, there's 11 times 4 of each kind, or 44. There's 44 of those. And I want 1 of them. And that was the one mistake that I had in that formula, is that these total numbers, I want 2, 4, 5 total cards. The total number that I want, and that makes a lot more sense, take that, multiply by 100, would be 9.5% chance in a 5-card hand that you end up with 2 of the 2 pair. Well, what other situations could we utilize this type of working with probabilities? So let's say we have a basketball team consisting of 10 boys and 8 girls. We need to form a 5-person starting lineup. What is the probability all 5 starters are girls? So the question goes, how many ways can we select 5 players from the 18, regardless of gender? That gives me my sample space. So that is just 18, choose 5. And once I have my sample space, or my denominator, my total amount, how many ways can we select 5 girls from the 8? Notice that it is more specific. We're not choosing from the 18 that's including the guys. Now we just want 8, choose 5. And so if we go, what's the probability that 5 girls start? Well, it's 56, which is 5 8 choose 5, all over 18 choose 5. If you type that in your calculator, you end up with 1 over 53. You can see that knowing how to do counting with permutations and combinations makes finding the different sample spaces, the different number of ways of arrangements, faster than if you were supposing like making a tree diagram or making a Venn diagram to count all of these different types of ways. Okay, what's the probability a basketball team consisting of 10 boys and 8 girls? Starting lineup is 5 players. What's the probability the starters are 4 boys and 1 girl? Notice now we want 4 boys. So the denominator stays the same, which is always good to say, like, we want the number of, what's the probability of getting 5 players? Will be 18 choose 5. It's not probability, it's the number of ways. In the numerator, I want 4 boys and 1 girl. So I have 10 boys, I want 4 of them. I have 8 girls, I want 1 of those. Those are independent, so we can multiply those two. That's the fundamental counting rule. And if we do all of that, we end up with 10 over 51. Now again, I wouldn't be a good statistics teacher for you guys if I didn't say at least one starter is a girl. At least one. I want you to think the complement, or 1 minus the probability of no girls. That's what we're looking for. Probability of no girls, which would be 5 boys. So we take 10 choose 5, 5 people start, over 18 choose 5, and we get 1 over 34. So what's the probability that we have at least one girl playing? Well, that's a 33 out of 34 chance, which is pretty high. Last one. It's a little involved, so I'm going to read it, and then we're going to walk through it. Suppose the school is forming a committee to review the dress code. We have 3 administrators, 5 teachers, 4 students from which to choose the committee. If we select 3 members to be on the committee, what is the probability we choose 1 of each? Okay, so we have 3 admin, 5 teacher, 4 students. That makes a total of 12 total people. 12 choose 5 is going to be my denominator. What's the probability I have 1 of each? Well, now I will have 3 choose 1 for administrators times 5 choose 1 for teachers, and we would have 4 choose 1 for students. Each of those are multiplied. It's 1 from each group, which would be 3 times 5 times 4, surprisingly. 20, 60 over 12 choose 5. That's why we need a calculator for this. So that gives us 220. Simplify that down, which is what the calculator is for. If you want to see me type this out, I'm going to go NCR, and you can actually just type that in. So let's hit on our calculator. We're going to hit Control Division. I'm going to do NCR, parentheses, 5 choose 1, times NCR, 4 choose 1, times NCR, parentheses, 3 choose 1. And then the denominator would be NCR, 12 choose 3. I hit enter, I get my percentage. If for some reason I needed that to be a fraction, I can take that number and go menu, number, convert, approximate to a fraction, hit enter, and I get my 3 out of 11. You see on the notes, that fraction simplified to 3 out of 11. If we're looking at this, there's another way to build this. It's small, but we could do a tree diagram. And this will get us the exact same result. It's just a lot more work. So you can see that utilizing the calculator is far more efficient for our work. So I hope these 2 videos kind of tied up loose ends on how to count, put these together to find probabilities. And now we are on to random variables. See you, Falcons.